Hello, welcome back. We are going to go from data structures to algorithms, and we are going to start with analysis of algorithms. Now, in this lecture, we will see what are the important points to note when we have to analyze an algorithm. Right? And in the next couple of lectures, we will be looking at different ways to analyze algorithms. Okay, so first question: when you are asked uh, asked to write an algorithm, you are usually faced with two questions. Okay, so one is, let me just note down. So first question is that should I write this algorithm which is easy for me to understand and easy for me to write down, etc., or should I write an algorithm which works very fast? Okay, so these are two kinds of questions which um, we will have to write an algorithm to which satisfies one of these properties, right? So an algorithm which should I write an algorithm which is easy for me to write, so easy to write and understand, or even debug, for example, or should I write an algorithm which runs fast? Now, what should you do? Right? You are let's ask you. I mean, you're taking an algorithms course because you might be want to take a profession where programming, etc., are involved. So this is a question which you will have to always ask. Now, so the main thing is that, see, if you are, let's say, I mean, why are you writing an algorithm? Maybe to submit as an assignment. So in that case, maybe this one will be enough, right? Easy to write an algorithm which is easy to understand and debug will be enough, right? Because it's that algorithm is going has only one purpose, and that's for assignment submission. But if your algorithm is going to work for a long time, the second one will be preferred, right? If you are going to run the algorithm for multiple times, like for example certain algorithms in your operating system, for working of your operating system, etc., in that case it's better that the algorithms run fast, right? So this is a design choice which is always with um, so a design choice for the programmers. Which should I opt for when I am going to write an algorithm? Okay, so as a best practice now, I would say first learn to do this. Easy to try to write algorithms which are easy to understand and easy to debug. That's the best. So like we said, right? We had used this thing. We have told this thing that when you are, it's easy to think recursively and it's easy to write a recursive algorithm. And probably I might have told you that, but recursive algorithms have a lot of it's I mean the computer requires a lot of effort to run recursive algorithms, and that slows down slightly your program. So if you are, as we mentioned, if you are going for a coding competition, it may not be worthwhile to write a recursive algorithm. Right. We have been writing recursive algorithms because those are easy to understand and easy to explain, etc. Right. Now, and also we have mentioned this fact that all recursive algorithms you can convert it into a non-recursive thing. Okay. Now, coming back. So if you are if you are a programmer in some company and you go join a company and then you are working there and you are writing programs there, algorithms there. Now you are interested in the second thing, right? Because your algorithms need to run fast. Okay, so you need to have an understanding of how to write an algorithm which runs fast. And secondly, what is this question of fast? Right? We need to understand what is this question of fast and also we need to understand how to write algorithms which run fast. Right. Now, so as I've been telling, as a best practice now, you for your it's easy to practice this, easy to write and try to write algorithms in this way. And once you have written that, then you try to convert it into an algorithm which runs faster. Okay, that will be the best practice for you to follow now when you are practicing. Obviously, once you have practiced a lot, you'll probably be able to recollect a faster technique. Oh, I can apply this faster technique and here and there, etc. So, okay. So we need to understand how do I say an algorithm is fast. So the question is that you need to understand how much time does your algorithm take, right? So if you can find out how much time your algorithm is going to take, then you can compare two algorithms. So there are two algorithms A and B. This takes this much, let's say 5 seconds, and this takes 10 seconds. You know which algorithm to choose. You have to choose the one which takes 5 seconds, right? So if if you have some tool to compare two algorithms, you know how to take this, right? So so we need to develop some notions on how to compare two algorithms, right? Now, so this comes to the question of what are the things which influence the running time of an algorithm. So let's try to list down those points which influence the running time of an algorithm. So what are the factors which are affecting the running time of an algorithm? Okay. One obvious factor is the input, right? So obviously certain inputs, if the input is very large, if you want to find out the minimum from a very large list, it's going to take some more time. On the other hand, if you want to find out the minimum numbers from a small list, it's going to take less time. So the input is obviously going to influence the running time of an algorithm. Two. Next thing is that how good you have written the algorithm, right? So it's the algorithm logic which you are going to apply. Have we used a binary search tree, or did we use we just used a linear search? So these are things which might influence the algorithm. So it's the algorithm choice, the how good have you written the algorithm, right? So the okay, so this we will call this as the time complexity of the algorithm, which is something we will come to soon. But this is basically the algorithmic logic. Okay, so that is going to massively influence the running time of an algorithm. It's clear to you. You could uh, I mean, you can always write a bad algorithm, right? And which takes a lot of extra time. Okay, now 3. Then there are a couple of things which are kind of not in your control. Okay, obviously the input is also not in your control, but something else which is not in your control, which is I mean, so you have written, let's say you have written a program in C, and then your C compiler is going to take some time, right? The C compiler is going to take that code and it's going to convert it into a particular executable file. Now, one particular C compiler will be doing one type of compilation. Another compiler is going to do something else. So maybe these two compiled code might be different and it might be taking different time. Okay, so the compiler so the compiler influences how it compiles. As we had this discussion that in one of the programming sessions, that we saw that the compiler does some optimization to ensure that the algorithm runs fast. Okay, For example, it manages the memory. It tries to manage the memory in 4 bytes. Okay, so that way it can try to run it can do some processing, memory management, etc. faster. So the compiler can do some optimization and ensure that things work faster. Okay. So the next thing is that, yeah, obviously the speed of your computer, right? How good is your processor and your hardware? If you have a good hardware, if you have a faster hardware, yeah, your algorithm will also run faster. Now, why is the software? How good is your operating system in enabling your program to be run? Or it can be software, it can be your drivers, or etc. So all the kinds of software, it can be your operating system or the drivers or the application, etc. you're going to use, etc. Right? So this is kind of the software part. This is the hardware part, and this is the compilers. These things are kind of, it does not matter in some sense, right? These are not in our control, because once you are written a program, it's supposed to run. It's supposed to run in any machine, right? And you should be able to compile with any compiler, etc. So these are things which are typically not. These are things which we won't be worried about too much, okay? And at least from an analysis of algorithms point of view. Okay, so on the other hand, these things will be like a computer architecture course might worry about how to speed up the hardware. An operating system course might be interested in how to speed up the working of your operating system, etc. Or your compiler course will be worried about how to ensure faster, better, how to compile your code and generate a better optimized code. So these are things which are dealt with in different courses, and these are, these are independent of how, what kind of algorithm you are going to use, etc. Okay, so these are things which we won't be interested in that sense. Okay, so our main aim will be focused on this, the time complexity of the algorithm, right? Now let's come here. Okay, let's come to time complexity of the algorithm now, and let's try to discuss on that. What do I mean by the time complexity of the algorithm? Now, we saw that obviously the input. So let's start with the input, right? Now the input is always going to ensure. Let me call t to be the time taken. Okay. Now the input is always obviously going to influence the how much time your computer is going to, your program is going to run, right? Now, okay. So for example, it can be that your you have a list of numbers, right? Maybe an array or a linked list, and you are interested in finding, let's say, the maximum number in that list. Okay. Now, obviously, it's going to, so now how much time does your algorithm take to run? It's going to depend on the input. So if the input is, let me just draw it. So we are interested in finding out the maximum, right? So 1, 2. Okay. Now, if the input is going to, if the input is like this, and you are interested in finding out the maximum, you can obviously you can write an algorithm which just returns the first element. So then it's pretty fast to do this. Okay, but that's not an algorithm which works in any general array, right? So if your problem is to take an array and return its maximum element, you will obviously have to go through the entire list. Okay, so no matter which n elements are there, you will have to go through the entire n list to find out the maximum element. Right? So in that case, in that sense, It's not the particular type of input which we are interested in. We are interested in how many numbers are there in this list, right? It does not matter if these are the numbers. All the most important, because whatever these numbers are, your algorithm is going to look at each of these numbers and decide whether it's a maximum or not, right? So the most important thing here is not these numbers, but how many numbers are there. So that's the most important input parameter for your algorithm, right? Now, so if there are so n numbers, our running time, the running time of our algorithm is going to depend on this n, okay, not on these numbers. So usually we will be writing like this: t of n to imply the running time of your algorithm. Is it clear? Now, so the running time depends on the input size. So this is the input size. Okay, there are n numbers, and this is, we call it the input size. Now technically this may not be the let's call this in the input size. Okay. Right. I wavered a little bit because for a exact precise definition of input size, you should also calculate how many bits each of these numbers also take. Okay, but we are not going to do that. We are going to see our input size as how many numbers are there, right? Now, so this is usually considered as the input size. So let's look at other examples. We did some tree traversals, right? What kind of traversals? In-order traversal, pre-order traversal. These are algorithms which we saw. What are the input? What is the input to that particular those algorithms? The input is the tree, right? And what is the input size there? The number of nodes, right? So in those programs, so in those algorithms, the input was the number of in the input size is the number of nodes. Okay, so in those algorithms also we are looking. So there the input size is the number of nodes in the tree. Now, so you can then therefore you can try to write the time to be a function which is depend on the input size. So this can be something like the time taken to run, let's say the maximum number. Finding out the maximum number can be something like, let's say 27 n. Okay, so 27 into n, let's say milliseconds. You might be taking this, or nanosecond to do this. Okay, or it can be something like 100 n square, right? Okay, so it could be anything like this. Now, okay, so this is one point. So the input, so the one point which I was trying to make is that the input size is a very important parameter on which we evaluate the time taken for running that algorithm. Now, the next point to consider is the following. Now, it can happen that, see, there are our algorithm might run faster for a particular kind of input and slower for a different kind of input. This is something which can happen. Now, you might have seen some sorting algorithms. Now, what is a sorting algorithm? Sorting is you are given a list of numbers, let's say like this, and you are supposed to sort it into 1, 2, 3, 4, 5, and 50. Okay, right? Now, your sorting algorithm will work faster for certain kinds of input and slower for certain other input. We'll go through some sorting algorithms a little later, but this is since you have already seen the sorting algorithms as part of your earlier courses, you might be familiar with this, right? So there are some for some input the sorting works faster, and so for some input the sorting does not work faster. So then in that case, what do I mean by the time taken, right? This is a question you will have to answer. So how much time does your program take? So that question, what do I mean by that? Do I mean that, so this question then comes out. So then there are usually there are three questions here then. Let me list down those three questions. And so the three questions there are, so there are three questions. The three questions are the best case time, or which, given the best case scenario, so the best case input, how much time does this algorithm take, right? Okay. So for example, in a sorting algorithm, it can be that already the input might be a fully sorted list. So if you are given a fully sorted list, your sorting algorithm is going to return very fast. So that can be the best case example. That can be the best case scenario. And then the question being asked is, in this best case scenario, how much time does your algorithm take? Okay, so that is one problem you can always ask. So given an algorithm, how much time does it take in the best case scenario? Next is the average case time. What is that? So this is probably the natural thing, right? So so what is average case time is, in average, how much time does your algorithm take? Okay, so this is, so so since you already have seen probability and things like that, you can see this, right? So this is kind of the expected time we are asking. Given this distribution, so the probability distribution of input, what is the expected time the algorithm takes, the program takes to run? So this is the average case time. Okay, now this is very this is a little difficult or complicated to analyze. So this is complex. What I mean is, it's kind of tough. It requires a little it requires a lot of effort to analyze the average case time, find out the average case time, just because you will have to work with probability distributions and etc. So this is very complicated. Now, what about the best case time is not really a good thing, because that's it can happen that the best case it works fine, and then for everything else it's too slow algorithm. Is that something you would want? No, you wouldn't want that, right? For some one case it's super fast, but all other cases it's super bad, not good algorithm, right? So this is not something you would want. Okay, you don't like this, but one can always ask this question of best case time, but this is not something you would want in general. So an average case time is something you would be fine with, but it's too complex to analyze. So we have the compromise thing is, we will always work with this. Okay, the worst case time. Okay, so what is worst case time? The worst case time is, for a particular input, the algorithm might be taking a long time, and in that long time, so what is that time? Okay, so finding out the worst case and analyzing its time is what is usually done. Okay, so you see, in the average case time, you will have to work with all inputs and then calculate its expected time. On the other hand, worst case time, you are interested in finding out one particular input in the worst case, where this entire thing will be find out the worst case input and calculate its time, the running time of that particular input. Is it clear? Yeah, this is good. Now, you'll see later that, for example, sorting like there's a sorting algorithm called quicksort. I don't know, you know this. Quicksort is a sorting algorithm, and quicksort in the worst case takes something like n square time. Okay, we will talk about the um, more formally on these things. So quicksort takes in worst case n square time, and the average case take n log n. So that is n into log n time. Right. Okay, and the best case also it takes n log n time. Now, so that's quicksort, and there are other algorithms which take different times for each of these things. Is it good? Okay. Now, so this is about time complexity. Next question is, so this, now based on your machine, etc., this might, so each algorithm might be taking something like, let's say something like 100 n square time. Okay, because for example, in your machine, a particular instruction might be taking something like 2 nanosecond. In my machine, it might be taking 5 nanosecond. So that constant difference might be there, and in the entire thing, I might be 5 times slower than your machine. So yeah, the time taken the time for taken for the entire program for me is 5 times the time taken in your machine. So there is this constant there. Now, we don't want to worry about this thing in our head, right? We don't have to want to think about, okay, I mean, because it does not matter. It's all about which machine, right? It's not studying the algorithmic complexity, right? So we will always be interested in statements like this. Okay, so this constant is not really we are interested in, because that depends on if someone later tomorrow comes up with a faster computer, this constant is going to change again, right? Because one instruction is now going to take less time, so this constant changes. So we have to come up with notations, etc., which forgets about this constant, right? This is what we would be interested in, so that we can just concentrate on the running time, the algorithmic complexity, algorithmic time complexity. This is what we can concentrate on, and we can forget about all these complexities associated with the compiler, hardware, software, etc. Okay, and therefore we want a notation which basically says the worst case running time of our algorithm is proportional to n square. Okay, so this is the thing. It's not, I'm not saying it's exactly equal to n square, some nanosecond or something like that. It's proportional to n square, where n is the input size. This is the kind of statements which we would like to make, right? And that's where our next lecture on big O and all these notations which are going to tell you about. Okay, thank you.